In this webinar, we're going to be talking about V8 Supercar design with CFD, and joining me for this webinar is Scott Birch.
Thank you very much for having me, Darren.
A little bit about myself first. So for those of you who don't know me, I'm a mechanical engineer and currently the Managing Director here at Applied CCM. And we do CFD basically, along with open source solutions. We are also the Pointwise distributor for Australia and New Zealand. And Scott is a mechanical engineering at Gary Rogers Motorsport, GRM. And his specialty is CFD and vehicle aerodynamics that helped the team develop the Volvo S60 V8 Supercar that they ran for the last 3 years prior to this season. And Scott also has the privilege of managing the two V8 Supercar development series for the future drivers and crew members. So the way we're going to do this is Scott's going to run through a presentation, take 15-20 minutes, and then I'll do some demos in Pointwise, showing you some aspects of meshing from Pointwise that are specific to the types of geometries that you see in a V8 Supercar. And then we'll have a question and answer session, and then hopefully wrap up on the hour. If you do have any questions throughout the webinar, feel free to type them into the question box. We've got Tammy that'll be moderating those and checking as you go through. So if you have any questions or concerns or anything, you can type them in, and then we'll try and answer as many questions as we can by the end of the webinar. If we don't get to your question while we're here live, they are recorded, and then either Scott or myself will follow up with you in a couple of days, depending on who's the best person to answer the question. So with that, I'll actually hand over to Scott to talk a little about aerodynamics of V8 Supercars.
Thank you very much, Darren. Thank you everybody for coming in today. Hopefully I'll be able to answer some of those questions you've had about the aerodynamics on racing cars. I'll run through a general presentation on the aerodynamics around a V8 Supercar, but a lot of the concepts will transfer to anything you're working on. So whether you're doing things like Formula SAE, or if you're studying F1 or even doing time attack cars, you can transfer a lot of the knowledge from what I'm showing you here into that sort of thing. So here I've got a little rundown on basically the makeup of the V8 Supercar. So it's a silhouette series where you have a car. It generally has the silhouette of your road car, but in actual fact underneath the skin they're quite a lot different. So the cars have common chassis. Basically the base chassis of the car can be is identical. You can repair, say, a Nissan on a Commodore jig if you wanted to. Where they differ majorly is things like sub panels for mounting your quarter panels, front panels, doors, that sort of thing. Getting into your body panels, you may remember if you followed the series in the last 15-20 years, we used to run steel body panels, but over the last few years it's changed quite a lot. We run mainly Kevlar exteriors on the car. About the only metal panels you'll see on the exterior are things like the 8-pillar bonnet, roof and the boot lid of the car. Down the bottom, this is one thing where CFD comes into its own with our series. Generally in racing you'll have a wind tunnel that's supplemented by CFD programs, but with V8 Supercars the wind tunnel testing is banned, mainly due to the expense of it, because we have limited testing avenues here, so there's not really a big market for keeping costs down on wind tunnel testing. So GRM not being the biggest team out there, we've still managed to utilise CFD quite successfully without throwing heaps of money into a computing solution. So here we'll start with aeroanatomy. So the parts that generally make up the V8 Supercar aerodynamics. Body positions, the first factor when starting a V8 Supercar, you'll actually get given the CAD from your manufacturer. Generally from about the grille downwards is where you're allowed a free-for-all. Above the grille it's generally a lot more controlled. You have to keep it quite close to the original car. Front bar there, if you look on the front bar of the car, and I'll sort of go through it when you see some of the mesh images later, you'll see we do change the shape of the bar quite a bit, and it does change with body position as well. Rear wing, every V8 Supercar's got a wing. Most of your race cars have a wing out there. There's seldom few that don't. we'll get into that. I'll show you some mesh images and we'll talk about rear wings some more later. It's usually good for balancing out the aero that comes from your front bar. Rear diffuser, it's an interesting one in V8 supercars, and we'll get sort of into that. They're generally a good tuning device for helping underbody flow if you're running cars with ground effect, and helping drive wing attachment, things like that. So preliminary CFD, when we started the Volvo program a few years ago, you don't go straight from manufacturing CAD to a finished CFD model easily. It's generally easier to start with sort of a baseline CAD geometry that's very easy to mesh to get ideas of how the car works. So where we mentioned body position earlier, you can see in the image on the left, we've got an example of the CAD and some of the constrictions you work with in the sport. So the body's lowered to a universal datum. So you take your CAD, you lower your body into the correct position so that roof height and things like that, you get an idea of that, you get an idea of bonnet height and boot lid height. One thing here, shifting the body backwards. The Volvo has actually moved backwards almost 4 inches on its wheelbase before we stopped. A couple of the reasons for that is maximising your splitter length. So you can see from the image on the left that we do have a fixed distance from the centre of the wheel to the leading edge of the splitter there. And you're generally trying to capture a high pressure bubble in front of the car, the stagnant airflow that builds up in front of it. You get that splitter length as long as you can to maximise the downforce you capture from there, and also increasing the under tray length underneath the car. And the other reason was the Volvo's got quite a stumpy rear end. It's actually quite short compared to the larger family sedans in the series. So it was good for helping get the bodywork underneath that wing at the rear end. This is one of the preliminary CFD models I used on the car. So you can see it's very easy geometry there. It was really quick to mesh. It was very not very intensive for computing time and things like that. So we're able to just take a standard supercar wing on the back there. That's actually just a VE supercar wing, and I was able to move it up and down and check different angles and see where we got the best sort of wing to body interaction on the car, where they would complement each other rather than just moving it right out of the way. Front bar, so I sort of go into a little description on some of the key elements on the front bar of the car here. So there's the front end of the car on the right hand side there. You see that great big front splitter and everything. So your front bar is the flow initialization point. So it's where you're setting up what's going to happen for the rest of the car. So changes you make on the front bar are very significant downstream. Creates a lot of downforce on it. You have the twofold impact of having the splitter that captures that high pressure bubble on the top surface, and it's also pushing all the air underneath there. So if you're thinking of things like Bernoulli's principle, you'll have the air rush under there and you'll have a drop of pressure as the velocity increases. Brake and engine cooling. So this will be an important one, especially coming up with rule changes. We're not only trying to cool down brakes, it's been better with the car of the future with the larger brake package. You don't have melting rotors like you used to get at Tasmania and things like that. Engine cooling will be a big one, especially with introduction of turbocharged cars coming back. So that'll make intercooler packaging and things like that pretty novel for us in V8 supercars. We haven't seen anything like that since the early 90s. The other thing with the bars a lot of people don't think about is withstanding impacts, and that doesn't just mean withstanding impact, it means making sure your bumper is up to the task. Sometimes if you don't, and I saw this on one of the early prototype models, our bars were a bit weak in the splitter department, and you get what's called porpoising, where you get a dramatic change in downforce as the bar closes in on the ground, and then you'll actually hear a quite terrible grinding sound when the car's doing 260 kilometres with that. You know, you have to make some changes to your composite layout. So 3 key elements with the front end of the car. Here we have the splitter. So this is an example of the mesh we use on the car. So that's a leading edge of the splitter on the symmetry plane there. So you can see probably one key aspect, especially if you're using finite volume solvers, so things like ANSYS, Cayless, that sort of thing. you want to have meshes that are adjacent to each other, quite similar in size. So you can see the ground element size isn't a great deal larger than the splitter elements there. So it stops you from having a rapid growth in your elements and then getting things like centroid skewness in your mesh. So it keeps things working quite well there. So you can see here the splitter actually sits very, very close to the ground. So you do need to ensure your mesh is a really good quality around this region of the car. So here's another part of the car that's quite important. It's the cheek of the bar. So you'll see in a photograph I've got later in the presentation where we were changing the cheeks quite a lot. We had different options for them, including up in the purple region there. You'll notice me pointing that out. It had quite a nice slopey front end on it before we filled it up with that to cut the drag on the car. So one important thing with the cheeks, and it's even with end plates on cars with front wings, is that you're trying to do a couple of things there. You're controlling drag of the car. One thing, you can see that little reflex that the mouse pointer is sitting over the top of now. It does a couple of things. It's generally kicking the flow to the outside of the wheel so that the turbulence on the wheel doesn't have too great of interaction and keeps the floor area as clear as possible underneath the car. The other thing you can do is you can drop the pressure at the back edge of your splitter there, so you can help with getting a little bit of extra downforce, and the low pressure that gets created outside the wheel region, if you kick the flow around, it helps for entraining some of the cooling flow for your disc brakes and things like that. So the under tray, you can see here on the under tray there's a little diffuser tunnel built into it. So diffuser tunnels are handy. Generally with your inflection point, you'll see your low pressure peaks on them. One thing that helps with flow attachment and efficiency on diffuser tunnels is the strakes. So you can see two strakes in the Supercar tunnel there. So they're handy for creating a streamwise vortex with a low pressure core that generally sort of helps keep the flow attached in there, and also the cores help decrease pressure through those regions, so you can generate a bit more downforce with them. There are some limits to how many strakes you use on the front. I generally see 2 is what most people go for. I've seen up to 3. On the rear end you can use a few more. So here's a pressure contour graph of what you're looking at on the car there. So you can see in the red that big high pressure stagnant air bubble on the front, and your splitter, you'll see if you can increase that splitter length out the front there, you'll just keep capturing that air. Generally there is a limit to it. If you can't balance it out with a rear wing, you will find you're too front biased on the car there. And then underneath you can see the blue region where the flow's accelerated and you've got the low pressure building up, and on the outside of the wheel you can see that low pressure built up from the cheek throwing air around the car there. Onto the rear wing, and this is something you'll see on every boy racer on the road, not that they know exactly what they're doing with the rear wing. So with a V8 Supercar, or in the Supercar series, wing profile is fixed, so you can't change the wing's onset angle, leading edge onset, to account for flow effects caused by, number 2, the highly compromised environment where the wing is sitting behind the glass house of the car. So your airflow is always changing at different speeds. Depends on the more modern cars, especially with raked windscreens and just the slopey bodywork tends to make it quite difficult in terms of the body of the car generating lift. But the other thing is it does make it easier for tuning your rear wings on your cars, keeping them out of the drag zone. V8 Supercars, you'll probably notice the wings generally aren't that high unless, I think the Nissans, they're quite high. They look like a top fuel drag car sometimes with their wing all the way up there. And the third point, all V8 Supercars use end plate mounted wings, which is an interesting point. It's something that I will probably get onto later in the piece, but generally with end plate mounted wings, they do offer a fair bit of stability with a car, and with something that's limited with things like flat floors in our series. The more stability you can get from a big end plate, the better. So here's an example of a mesh we've done on the leading edge of the wing. There you can see the 2D T-Rex mesh there, so you can see that nice clean mesh marching out from the leading edge connector there. Underneath there you can see the mesh deck lid extension that we did on the Volvo. It sort of popped out about 6 inches, and funnily enough we didn't even realise it till we put the cat over it, but the boot lid extension finished right where the Commodore boot lid finishes, so that was unintended. That actually just came out from the aero testing. So here's an example of a few streamlines and pressure contours that you see on the car. So you're dealing with quite a tricky region of the car. So as your airflow's thrown out of the way at the front, it converges at the rear. So there's a lot going on in terms of trying to control the airflow, especially with end plate mounted wing. You can see it's quite turbulent around the tail light region there. On the top of the wing there you've got your high pressure build up, and then underneath the flow accelerates and you've got your low pressure there. One big thing with an end plate is you're generally sealing your high and low pressure regions away from each other, so you don't get vortexes intertwining, I guess, on the side of your wing and lowering its efficiency. So it's a good way for race cars to increase wing efficiency. So rear diffusers. Rear diffusers, they're quite effective on a V8 supercar, not so much because we lack flat floors. So one of the key things with diffusers in our series is it decreases basal area. So it's basically reducing the amount of choking on the airflow in the wake of the car there. So we're just basically trying to get it out of the way, and it's quite a popular thing I think on the new 911 RSR. You'll see there's almost no bodywork below the centre of the spindle on the rear end of the car there. So the diffuser can help with increasing downforce, basically by acting as a venturi for helping the exiting flow on the car. One thing you'll see when we developed the Volvo, I did want to put strakes and things on there to increase its efficiency, but I was told it was basically painting a target on the car, because we do get quite violent out there, so you don't want people black flagging you through the race. With tuning the balance on a diffuser, generally diffusers in a lot of rule books I've seen, they generally limit the height of a diffuser. So you can play with things like departure angles and length. With the supercar it's a bit more difficult, and you'll see why in the next image. The silver mesh in there, that's actually the crash structure of the car, and then the yellow is the under tray or the cradle underneath the transaxle. So it's quite difficult to get a diffuser of any decent length in there. So you can see it actually just spans right up and gets out of the way of the rear end of the car. Probably one interesting thing, if you are using a meshing tool like Pointwise, on the corners of the diffuser, if you are having trouble getting a clean mesh through there, you can go to advance in front method to sort of clean up your edge elements there, which works quite well. So you can see really nice boundary layer growth on the floor there as well. So here we go. So I've got the diffuser and wing highlighted. So this image sort of shows how your wing and your diffuser are working in tandem. They work together to help drive the flow upwards. As I said, it's difficult on a V8 supercar because the diffuser's not quite as active because your floor's got quite a lot of elements under there. If you've got a flat floor car like a GT3, it's generally much more effective having a diffuser in there, and if you can get a wide diffuser with lots of strakes in there to stop the turbulence from the wheels and things getting in, it makes them even more effective. So the joint solver, so this will answer one of the big questions probably with why we all have end plate mounted wings on these cars. So the joint equations for the incompressible turbulent Navier-Stokes equations are solved in this. The joint formulation is time symmetry preserving, i.e. conserves kinetic energy, and allows for the calculation of surface sensitivity. So this is something that Dr. Stevens lent us for the purpose of analysing some of the VE aero back in 2012. So you can see on the surface contours there's some red patches, and the red patches are are generally showing areas where you can push and pull panels to get the maximum change overall for your aero on your vehicle. So here's the example of the vectors on the surface there. So they show where you can move surfaces on your vehicle to increase the drag. And when we put them over top of each other, you'll see that the deck lid extension on the Volvo sort of mimics the extension of those vectors. So you're probably wondering why on earth would we purposely put body panels in the way of somewhere where it will drastically increase drag like that. And part of it is to do with this process here, homologation. So we go out to, this is Sail RWF base, go to a test speed of 200 kilometres an hour, so we just have a diff ratio in the car and it just hits the limiter in fifth gear. And then we have a coast down test for drag, and downforce is calculated through suspension compression on the car. So we do have mandatory drag and downforce figures we have to meet for the category in order to have our car signed off for its body development. So if you've got drag, put it at the back. So that helps explain that reason why we have that interesting deck lid extension that is basically trying to catch drag at the end of the day. And the other point is centre of pressure. So trying to get your centre of pressure rearward on the car, especially behind your centre of gravity, helps create an aerodynamically stable vehicle. You can actually see in the photo below where the contouring on the cheek was previous to us inserting our little. That's actually just a foam piece just to help play with the drag. So that's actually the final cheek that we ended up with in the car. Okay, that's it for my presentation. Thanks for listening. I'll hand it over to Darren now.
Okay, so Scott's just talked about parts of the car. I'm now going to pull up some of those in Pointwise and go through a bit of a demo talking about the different meshing aspects and what's important there. So what we'll start with on this one is we've actually got half of the rear wing. This is the one off the BE, so you can actually see the piece in the middle there is where the centre mounts would be. So this is not an end plate mounted rear wing. And the box you see around that was just a region I put so I could actually generate a volume mesh on the laptop for the webinar. So what we start with is you start with putting a surface mesh onto the grid, onto the geometry, and then I'll just show here. So the end plates have a thickness of a few millimetres. We actually mesh those, and you can see it's not fully resolved here because it's only one element thick, but yeah, they're in the geometry. And the thing to note here is we're using quadrilaterals on all the thin pieces rather than triangles. And then on the end plate itself, we've just got a quad dominant surface mesh. And then at the moment on the actual wing itself, we've just got a Delaunay triangulation. The interesting thing with that is you can actually see here there's the curvature of the leading edge of the wing. It's not really resolved using isotropic triangles. And so what Scott mentioned in the presentation was he was talking about using 2D T-Rex, which is a Pointwise technique, which is anisotropic tetrahedral extrusion, which in 2D just extrudes anisotropic triangles, and we can use those to give us stretched elements that are stretched in the span-wise but compressed in the stream-wise direction to allow us to try and capture that curvature. So an example here is if we take this and we go grid T-Rex, I've got set here, it's set to triangles. If we set it to triangles and quads, set how many layers we want. So these are the number that we're going to extrude off the leading edge. And at the same time, we need some boundary conditions for the extrusion. And so we actually set for the leading edge and the trailing edge, we can set a size. These are in millimetres. So this is the initial cell height that we want there. And then on the end plate, we just have a match condition which I'm trying to see. It's just called match, so they're highlighted in yellow. And so at that point we come and initialize, if I've got it all right. What you'll see is Pointwise has gone, I'll select OK on that so we can actually see the mesh. You'll see that Pointwise has actually gone and it actually extrudes anisotropic triangles, but I told it that it can combine those into quadrilaterals, so it notices it can combine into beautiful quadrilaterals there that come off, and then you'll see as it goes around we get the quadrilaterals at the back, but we end up still with the tris in the middle, and that tells me I've actually done something wrong because I know I can actually get quads in there, and the reason is that I've set the type to Delaunay and it's set to triangle. So if we actually change the type across to advancing front ortho, which is just a different triangulation method, allow it to be triangles and quads, and then hit initialize on that mesh again, you'll actually see this time we almost get a perfect quad mesh. We still have a few tries in there, and that's because of the growth rates coming in there. If you're an advanced meshing person or a CFD person that's been doing meshing for a very long time, you probably say to me, hey Darren, that's actually a rectangular surface, we could have just done a structured mesh on that. And the answer is, yes you could, but in this case here, there's a couple of clicks and I've got it without having to think too hard about it. And I can do the same for the bottom, and I'll do that here. So again, these numbers I've come up with through previous work, and I've got a growth rate here. This time I'll try and remember to get all the settings correct first go. And again, it's just setting the boundary conditions, which are the same boundaries in this particular case, so I don't have to change them. And hit initialize. And did I remember to do it? Yes. So now we've got a nice quad mesh, or quad dominant surface mesh with really good curvature resolution at the front leading edge, and it's all quad all the way through there. So the last step then for something like this mesh would be to actually do the volume mesh, and this time we're using T-Rex, but you'll notice I've highlighted white there is actually the block or the volume. So this one here, we come in, we're going to say we want all tets, pyramids, prisms and hexes, so make whatever elements you can. Under the advanced, we'll adjust, we've got a collision buffer, and I'll show that when the mesh comes through. And then there's a skew criteria, which is a max angle. So this is the maximum internal angle that any tetrahedron could have in the T-Rex side. We've got a growth rate and a maximum layers. This time the boundary conditions are actually done for the 2D grids. So you'll see the wing here has an initial height of 0.25 millimeters. On the end plate, we set the same condition, and then everything else is pretty much, on the symmetry plane, it's just told to match. So as they grow out, you'll see the symmetry plane get adjusted. So we're going to hit initialize on there, and that'll start running any second. And so what you start seeing, Pointwise show in white here, is just the front of the inflation layer as it grows out. You'll actually see that because I'd initially done this mesh before, the symmetry plane currently has the final shape, so you can actually see the front tracking through the layers. At the moment we've got no red spots appearing, they're about to start appearing, you'll see up here, and that's where the inflation layers will start colliding, and so Pointwise stops inflating at those points. And that's where that collision buffer comes important, to tell it to stop and leave enough room to fill it with isotropic tetrahedra at the end. And they'll start stopping at the front here because the cells have actually reached an aspect ratio of 1, meaning that their height is the same as their base length. So at this point, T-Rex is just finished, and Pointwise is now just generating the volume mesh. It's going to take an extra minute or so. So at this point we can come across here and say we've generated a total of 845,000 cells, 235 of those, 1,000 of those was in the boundary layer region, so from T-Rex, and we got 7 complete layers, but a total of 15. So the complete layers would have been up to the point where they stopped, and then after that it's just partial layers. So if we go OK on that, then what we want to do is we want to go and do some examining. Pointwise is quite powerful. You can examine a lot of metrics for cell quality controls, etc. In this particular case, I'm just going to look at the cell type, because I want to show you the different cell types that have appeared. And I'll just get rid of the surface mesh. And we'll turn off that. So I've got a pre-cut here. So if we actually look at a cut through the middle of the wing, the colours are the cell type. So blue, hexahedra, yellow, pyramids, red, tetrahedra, and if we look carefully enough, there's a couple of green ones in there, which are triangular-based prisms. And so what you can see here straight away is our beautiful quad mesh has allowed us to extrude pretty much 7 perfect layers of hexahedral cells, and then Pointwise automatically goes and puts the pyramids at the tops of those layers to join onto the tetrahedra. And you can also see at the back that we wrap up and around the lip, and the 2 fronts that would have been coming off the back of the lip and off the top edge of the wing, they would have collided in this region, and that collision buffer has allowed us to adjust the spacing to ensure that we can get tetrahedron in there without completely destroying the quality of the mesh. So that's looking at that direction. If we then look at a cut from the other angle, we can actually see that we've done exactly the same. Goes off the top of the wing, up and over the end plate, and you can actually see it grows out of the join between the end plate and the rear wing.
Yeah, and I've just mentioned that being able to have a really good boundary layer mesh like this, especially on your end plate area, helps to capture those viscous forces from the vortexes that form between the wing and the end plate there. So really important for getting a really good resolution on the energy inside your vortexes and how they affect your downforce.
And what I'm not showing in these cases is we can also put point sources in to then control the downstream resolution to ensure that those vortices are actually, that start on the leading edge and then resolve rather than dissipated in the mesh being too coarse. So what I'll do now is pull up the other one, and of course I always pull up the wrong one. So the next example, I've only got 2 examples to go over in a short period of time. So the next example is just a generic sedan geometry. It's a CFD person's dream because it has no wheels, has no exhaust, has nothing in it except beautiful surfaces. And this geometry is nothing special. It is used in the Pointwise training to demonstrate T-Rex. And so what I'll do is I'll switch over. And so what I'm going to talk about here is the choice of element types to minimise the number of cells that you have in your simulation, but at the same time maximise the accuracy of the simulation. So traditionally when you're doing external aerodynamics, you're going to be putting it in some sort of wind tunnel or effect like that. And so what we've got here is all these green regions are perfect hexahedra. So what we've done there is we've fully structured meshed all those regions because they're going to give us the best accuracy for the lowest cell count. And then the purple region is the region around the car. And yes, this sedan you can probably sit down and do a structured, perfect multi-block structured grid, maybe in a few days, a few weeks or a month, depending on how expert you are at that type of gridding. But nowadays most people use unstructured meshes. And so in this case again I've used quad dominant, which was a feature that came out in Pointwise version 18 back in September last year. And that allows us to get predominantly quads on the surface meshes of things. And then what we've done is we've made a block using the quadrilateral meshes from each of those other domains. So you'll see all the green ones around the sides where the blocks join together are the quad meshes and they're node matched. And then what we do with this is, the purpose of this one is, again, we can use T-Rex to do the volume mesh. I'm not using 2D T-Rex in this case. So we're going to convert all wall domains, everything. Again, 15 layers is what I've set. You could go more. The code will stop when it gets to an aspect ratio of 1 anyway. And growth rate of 1.2. Any higher than that, you tend to be a little bit aggressive for most CFD codes. And then in here, I've got the collision buffer set to 2. That's to give me a little bit more space underneath the car where it comes off the floor of the car and the floor of the tunnel. And then again, you set the boundary conditions. In this case here, it's in meters, so the tunnel floor is set to an 8mm initial height, and then the sedan set to a 5. So it just shows you can actually have different sizes. And with that, I'll just hit initialize. And again, we will see the mesh growing off the car.
It's much quicker than mine. Mine take about half an hour to 40 minutes.
Yeah, but you're also running tens of millions of cells.
Yes.
So you'll see the red points are where the inflation is stopping. And that's because it's either reached a quality criteria or it's actually reached a criteria that you've set in terms of how many layers you want, etc. So there you go, that's mesh that. So total cells is only 500,000 in this case. We got 4 complete layers, a total of 13. And so the last bit to do again is we just examine. I'm not showing you a mesh quality in this case, but we're just looking at some predefined cuts. And again, we'll turn off the surface mesh. And so what you want to look at here is you can actually see we've grown, again, blue is hexahedral cells, right? The yellow are pyramids, tetrahedra are red, and the prism, triangular-based prisms are green. So you'll see that we've got blue off the car. In this case, where I've cut through, there was no tris on the surface mesh, so you get a blue inflation layer. You get a few triangular prisms down here because obviously there was a triangle on that surface. And then off to the side, you'll see we get this hexahedral mesh there, and then we get pyramids matching up to the quads. And the one thing that I didn't do here, which I'll go and redo, is if I actually take in the other block and we examine the cell type and go back to my predefined cut, what I wanted to show you is if you didn't know that there was a join between those meshes there, you will actually see that Pointwise has matched the mesh coming up off the floor in that unstructured block with the hexahedras there. So you actually get a one-to-one node, no interface. It's a perfect node or conformal mesh between them.
Mm. So that'll be really handy for people out there, especially using your open phone-based solvers, or in a lot of meshes. If you're trying to match a grid to an unstructured mesh like this, you will have issues at the join there. So it'll be really effective for you guys. If you look down at that floor mesh, it'll be really handy, especially if there's anyone out there who's trying to validate wind tunnel results or try and replicate wind tunnel results on CFD. You want to be able to get a really good resolution of the boundary layer in the lead up if you're not using moving ground wind tunnels.
Yeah, so, and all I was doing in these other 2 cuts is just showing you, if you try and work it out, there's roughly 2 tetrahedra in between those 2 fronts. You get a few pyramids in there, but that's because the code has to stop put pyramids to join them on. And so, you know, in the regions where you've got your boundary layers, you've got really high quality hexahedral cells. And yes, I could probably use a much smaller boundary layer thickness here, etc. But it was done for the purpose of doing it on an iPad, MacBook Air. So with that, what we're going to do is we'll actually pretty much go and see if there's any questions. So we haven't had any questions come through yet. So with that, I'd actually invite you to type away if you can. So, yeah, if you...
I won't have any numbers or figures to give you, sorry.
Scott will make them up anyway.
Yeah, I'll just lie.
So one of the things that often gets asked, this was really looking at the usage of CFD rather than getting into the nitty-gritty technical details of the CFD. So no doubt someone's probably going to ask Scott what turbulence model he uses. So rather than waiting for that question to come through, Scott can answer that right now.
Spell out Elmaris, single equation.
And I know for a fact that when I first met Scott, they were doing about 300 million cell meshes.
Yep.
And that's because they were running with a Y plus around 1.
Yep.
And subsequently they've switched to probably running about a Y plus 30 with a wall function.
Yep.
And that allows them to bring the mesh down to what, about 60 million? Or?
Yeah, yep, around 60 million.
So, that, and realistically there's probably not a lot of difference between the results. So going from 300 million down to 60 million, it's the way things go. I've got a question here, but I've just got to expand it so I can actually read it. Can you find the drag coefficient directly without doing CFD? So you could probably do that with working out a frontal area from the car and then from the actual down the coasting.
Yeah, the coast down test. It's actually surprisingly good. The coast down test.
And realistically, with all CFD, you usually have to do some sort of validation, and it's quite difficult because, as Scott said, the wind tunnel testing is banned, so you can't actually go and put one of these cars in a wind tunnel, get accurate forces, lift, drag, etc., and then compare to your CFD. And so, in a way, when they do the tests for the initial aero tests down at the Air Force Base, etc., the drag force and the lift force they measure there is what they actually compare back to the CFD. And then they make changes to the car and see if the CFD, how well the CFD goes at predicting those. So it's probably closer to what you get with industry. It's often quite difficult to do good validation for industrial problems. So we got another one. How do you measure aerodynamic forces accurately using data and suspension? That's nice and long. Hang on, if I double click potentially on
it's very difficult because you have to take into account the noise that you're getting in your data. So you have to account for things like roughness of the surface you're driving over, crosswinds, especially at airports. It generally comes down to doing multiple runs back to back, and you have to sort of take the data you get with a grain of salt. You have to know, you have to be able to say, okay, we roughly know where we're going with this. It is quite close. I mean, you see the series after we tested three cars in one weekend at the RAAF base and put them all on the track. You can see an entire field of cars, 22 cars that are separated by less than a second. So it's scary how equal they are out there. It comes down to the driver a lot. Got another question coming through.
What do you favour, adherence, negative lift, or drag reduction?
It depends on your circuit. Generally, it's difficult to go reducing drag on the car. Whenever you're reducing drag, you want to make sure the efficiency, so your lift or your negative lift on drag ratio, you want it to be better. So if you're taking off drag, don't do it at the expense of downforce on the car. There are some people that like to go the slippery setup. If you tell the driver you've taken some rear wing off to make it slippery, they'll generally start begging you to put it back on again, especially with these cars. If you talk to people who've hopped out of a Lamborghini GT3 and they jump in a supercar, they say they're a hell of a lot of fun, but mainly because they don't stick to the ground all that great compared to the GT3 car.
And the second question we got there is you use the Spallet-Amaris with wall functions. Which model did you use when you're at y+1? It was actually Spallet-Amaris in both cases.
Yes.
So you can use Spallet-Amaris itself was originally done for without wall functions. However, the implementation that we have in Caylus does allow usage with wall functions. And so we've done a fair bit of validation with Spallet-Amaris in different turbulent flows with different Y+ values to ensure that you actually get the correct friction still as you change your Y+. So yeah, Scott started with Y+1 Spallet-Amaris, and he's still using Spallet-Amaris, but now with a Y+ around 30, and having much less runtime because he didn't change the size of the computer, but he reduced the mesh size significantly.
Yeah, that's a good question. Thanks, Joan.
Hang on. So the other question is, how in depth can you get with aero on a race weekend, i.e. using all this software?
It's difficult because I travel with the team, so I can't jump on and start doing CFD while I'm there. Sometimes I have been workshop-based when events have been on, and I'll see something and I'll have something run and see what people are doing with it by the next day. If I want to test out something that I see another team having a go with. So that sort of covers using the software. With testing developments that we do, it's quite hard because they're starting to limit practice time quite a bit, and that's generally the only time you can get out there and physically test components you develop, whereas F1 have a lot of scope for testing their aero developments.
Yeah, so the CFD is usually not done on the track, and a lot of the times GRM would do a lot of different configurations and use the CFD to give them what you'd probably normally get as a gut feel after observing the car and tweaking a car over several years of going through the races. So you can go into some of these pits where you've got some very experienced race engineers that have been working on the same car for the last 10 years or so, and they'll know what they have to do to tweak the car to get it to perform. They won't be able to tell you from a shear stress or flow separation or that sort of stuff because they don't get that insight from just observing on the track. But GRM essentially uses CFD to build up a lot of that knowledge so that their race engineers have that experience with a relatively new car very quickly. And you saw that with the Volvo, right? It hit the ground running in 2014 and it performed pretty good straight away. The aero side, they had some issues with engines and stuff, but the CFD wasn't done on the engines.
Yeah, I'll say one thing with that is, one thing I always mention is CFD or wind tunnels explain the what and CFD explains the why. So it generally reveals a lot of the sort of intricate little tricks to how the aero on your car is behaving. And sometimes you'll go out there, and like I said, with aero testing at an Air Force base, it's very difficult to get a super accurate read on what's happening with all the noisy parts in your environment. We even had the car start increasing front end downforce at one stage, and we couldn't figure out what was going on because we hadn't changed anything. And it turned out it was the rubber on the tyres wearing off. So there's a lot out there that's very hard to take. So you do take educated guesses once you understand what's happening with the behaviour of the car through CFD. So it's handy for that.
I guess the next question here is, any thoughts on implementing automized shape optimization for a certain variable, i.e. having the solver determine new shapes, features of the geometry. For V8 supercars, probably difficult considering the shape is pretty much controlled to some degree.
Yeah. That being said, I'd definitely look at it, especially if somebody came ringing up tomorrow and said, we'd like a car entered in the championship next year. It would definitely be something that would help you out a lot.
One area where we have actually looked at it, and I guess that's where we looked with the adjoint solver originally, was the brake ducts, because the cooling to the brakes, that's all underneath, and that's actually not a controlled item. So GRM have the flexibility to design those brake ducts how they like, and they actually are bifurcating ducts. So they come in as one and then they split into about three to,
I've got
the
it down
VE
to
did
2
3,
now.
you've got it down to 2 now. But and clearly you want uniform airflow through each of the ends of that. So that's one area where I guess optimization, and that's where you'd use something like the adjoint solver results, which gives you surface sensitivity, and then you link that to either a mesh morpher or you could actually come back to remeshing, depending on how complex your geometry was with Pointwise. If you'd scripted the geometry creation in Pointwise and the meshing, then you could potentially have that come through. So, why improve develop aero through the season, even when you're confined by aero parity?
So there's a few things you can do with there. So one of the big things is getting an idea of the dynamic behaviour of the car. So the car's not just sitting there 50 millimetres above the ground all the time. It'll be banking. You'll have effects from different modifications. So you could even change the exhaust and have a significant effect on the aero of the car in that way. A few things you're allowed to do for tuning the car, as Darren said, brake ducts. You can also change your intake ducting. Get an idea of things like blanking for, sometimes you'll blank the engine right up to go out there for just one hot quali lap, and you can make quite a bit of extra downforce that way, and it's good to get an idea of what you're up for when you head out like that.
All right, I'm going to have to draw a close there because the webinar software is probably going to kick us off.
Yep.
We've pretty much reached our hour. So with that, I'd actually thank you for attending the webinar. As I mentioned at the beginning, the recorded video of this webinar will be available. It'll be on the Applied CCM YouTube channel, and for those who registered with an email address, you'll get an email with a link. If you have any questions about Pointwise or Applied CCM, please feel free to email me, and my email address is on the screen there, d.stevens@appliedccm.com.au, or if you have any questions about Gary Rogers Motorsports or I guess the V8 Supercar series, then please feel free to email Scott, and that's his email address there. If there was a few more questions that have typed in the system, we didn't get to answer them tonight, then either Scott or myself will follow up with you in a few days' time. If it's got to be Scott, it might be next week because he's actually at Formula One tomorrow here in Melbourne, setting up for the V8
I'll be having a very good look.
So Scott won't be looking at anything until next week, but if it's something that I can answer, then you'll probably get an answer before the end of this week. So with that, I'd like to thank you for your attendance, and that concludes tonight's webinar.
Okay, thanks everybody.